So we're going to call this Graphing Trigonometric Functions Part 1. We're going to start real basic, and we're going to go back to the unit circle for a moment. We're going to talk about why the sine function graphs the way it does and why the cosine function graphs the way it does, and same thing with tangent. So there's some links up here on the screen. You're welcome to try to copy and paste those somehow if you'd like, but I'm going to skip over the actual lessons there, or the clips from those links, but I'm going to talk to you about hopefully something that's a bit of review for you, especially since we've talked about the unit circle quite a bit. Alright, technology's not working for me today. Alright, so let's first talk about the sine function. So when we're graphing the sine function, maybe you have a shape of it in your brain from a previous math class. You kind of remember what it's going to look like. But what we have to remember is that the sine function are the vertical changes within the unit circle. So remember, vertical change is synonymous with the y values. So if I think about being on the unit circle, and if I was going to create various triangles throughout this unit circle opening from standard position, the y value, like here, would be a 0. And then, you know, as you, oh geez, it's supposed to be vertical. Alright, so these are supposed to be vertical lines. I'm just going to warn you now. So these are all going to be vertical lines. It's the y value. And then up here, remember the y value on a unit circle is to be a 1. So it starts off at 0, goes to 1, and then kind of comes back down, and gradually the y values become smaller and smaller until they get back down to 0. So if I look at continuing with the unit circle, the vertical changes here, like this is still 0 here, but then if you, I should have done these in opposite colors, it would have made more sense. These vertical changes are all negatives, because like down here the vertical change is a -1, and then it keeps getting closer and closer back to 0. Like those are supposed to be vertical. Alright, so if I try to take these angle measurements and then relate them to the change in the vertical axes, how tall each of those lines were, I think about graphing that on this, it's really a coordinate plane, right? So, face is going to get in the way here. I noticed that the beginning part was 0, and then the highest the y value got was 1, and the lowest it got was -1. So if I think about the range of this graph, it went as high as 1, it went as low as -1, and then 0 was kind of the pivot point where it went from positive to negative at some point. So this first red line I tried to draw was a height of 0. So at 0 degrees or 0 radians, it was a height of 0, and then it kind of gradually went up, 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 until it got to, remember this is our friend pi over 2. So at pi over 2, it was all the way up to a value of 1, and then it kept going smaller and smaller and smaller and smaller until it hit pi over here. And at pi it was back down to 0. Well, then it started to go negative. So it got larger, well, more and more and more negative until it hit, remember this was our friend 3 pi over 2. So at 3 pi over 2, it was all the way down here at -1. And then back here at 2 pi, it came back to 0. So, drawing on a tablet, keep in mind, we'd get that shape, which we know is the sine shape. For a lot of the kids, you just kind of memorize the shape where sine starts at 0, and then it does this really cool cyclical curve. If we were to measure in the negative direction, it would have been these same green lines, so it would have been like, whoops, dropping down like this, and we would have created the rest of the sine function. Remember, it's a continual curve. It never begins or ends unless we restrict the domain. So that's how you can interpret the sine function. It's the y values off of the unit circle. So cosine are going to be the horizontal changes, which are the x values. So if we think about here at 0 radians, the x value is all the way over here at 1, and then the x value at various radian measures. Oh gosh. Super well drawn, as always. They get smaller and smaller until they get all the way up here, where at pi over 2, it's going to be an x value of 0. Hello, little daughter. Alright, so then if we continue on here, oh goodness, so very, very ugly. The x values, oh, you know, I should have switched colors. The x values in this direction they are going in the negative direction until you get over here at pi, hi baby doll, where the x value is a -1. So for the x values, they're still going to be positive, because think of the coordinate plane going to the right is positive. So down here at, if you want to call it, you can either measure this negative or you can call it 3 pi over 2. But either way, 3 pi over 2, the x value is back at 0 here, or 0 here. So if I think about what's happening as far as the range of my function. Hi. Isn't this cool stuff, Natalie? Yeah. It went as high as 1, as low as -1. This was 1, this was -1. And then 0 again was kind of the pivot point where my function is going to change somehow. And I think about those quadrantial angles that we talked about. Right here was, let's call it -pi/2. This is 0 radians. Something happened at pi/2, at pi, at 3 pi/2. You can keep going to 2 pi if you'd like. And I think about what happened. So at 0 radians, it was measuring all the way out to 1. And then at pi/2, it came back down to 0. At pi, it went all the way down to -1. Oh, you okay, buddy? At 3 pi/2, back to 0. And then at 2 pi, if we ever get there, I never showed that here, but it would have came back to 1. So if I look at the shape here and what's happening is I get this lovely, what most kids refer to as the horseshoe one. And then the more we learn about sine and cosine functions, we realize, gosh, they're really just the same thing, just as far as shape goes, because if I think about bringing this guy back, it's just kind of a sine function that's been phase shifted. We'll learn that word in a minute. Oh, I need to back up a screen. I didn't talk about whether sine was even or odd. So since sine has symmetry of the origin, it is an odd function because it's got a symmetry of the origin. Cosine function, however, has symmetry with the y-axis, so that would be an even function. To relate that back to an old topic. All right, so now my friend, the tangent. So the tangent function is the slope as your degree or radian measure changes. So if I think about the slope here at 0 radians, the slope of that little horizontal piece would be a slope of 0. So 0, 0 if you want to write it as an ordered pair. And then if I think about the slope of each of these lines as I keep graphing them in, they keep getting steeper and steeper and steeper, so getting larger, until the point where they become undefined. So at pi/2, it's kind of weird to write it as an ordered pair, but basically my function for tangent is undefined, because it's a completely vertical component for slope. And then if you kind of keep going around the unit circle all the way to pi, switch colors, this guy, so bad. It's going to keep getting less steep until it gets all the way back to 0, but notice the slope here, they're going to be negative. So like whatever angle measure I just tried to draw on there, maybe the slope is like, -1 or something, but it's going to keep coming all the way back to 0. So if we think about continuing on here, our tangent function is also going to be undefined right here, which is at 3 pi/2. So what that means for tangent is, if we were to graph, and I'm going to actually go back -pi/2 as well, we'll see a pattern. Eventually. Where if I think about graphing something that is undefined in value, that means I have a vertical asymptote typically. I have some sort of discontinuity, but for these guys, it's a vertical asymptote. So at pi/2, and if you think about going backwards at -pi/2, and then at 3 pi/2, I have vertical asymptotes. And then I saw that at 0 radians, it was a measure of 0 for slope, and at pi radians, it was a measure of 0. So what happens is if you try to plot a whole bunch of points, you'll see that tangent, nailed it, even on a tablet, go me, looks something like this. Hey, baby doll.
I did my hair.
You did do your hair, it looks beautiful. So is tangent even or odd? It has symmetry of the origin, which means we have another odd function. So that was a little intro as to what the sine, cosine, and tangent basic functions look like. What we're going to do now is we're going to look at our notes, which I apologize in advance. I think I updated the notes, or Mrs. Hoffbauer probably updated the notes. We're only going to talk about general trig functions today. Yeah. Oh, chocolate.
Can you have one?
No. We're not going to talk about phase shifts in this lesson. If you're looking for a lesson on phase shifting, I would like you to go to the next one. It's probably called Part 2 or something, 4.4 Part 2. So this screen talks, basically it's all the properties of the functions that you're going to see on some like purple formula sheet I'm going to give you. Yes.
I got a computer. My help.
Okay. So this is kind of hard to read, but at least the general shapes are on there on your formula sheet. This is actually from your notes. So the beginning of 4.4, they give you the sine and cosine functions, and they give you the complete function, the general form, in both factored and unfactored form. So this is the non-factored form. This is the form that I prefer like 100% of the time. So I'll even add an extra set of parentheses inside the cosine and sine functions, where the b value is factored out if there's a phase shift. So if there's no phase shift, then, oh, there's a typo here, by the way. The phase shift would just be C. I don't know. I'm not sure what's going on with that typo. Anyways, I'm sure I fixed it on your notes, right? Totally. So we're going to often be given functions that are in the non-factored form, and then I'm going to expect you to factor the b out, and then you can see the phase shifts a little easier. That's the way I always do it. Some vocab words for us. Amplitude is the power of the wave, so it's the measurement of midline to the max or midline to the minimum. So they should be symmetrical because of the shape of the graph. And I always refer to it as the power of the wave because I think that helps if you think about like an actual wave, like a tsunami wave. You know, the larger the crest, the more powerful it is. Let's see. Remember, the amplitude is the absolute value of a. So if there's a negative in front of the function, like a -3, the amplitude is just 3. The negative refers to a vertical reflection. The period of sine and cosine is generally 2 pi. However, if there's a b value in your function, that shortens or lengthens the length of the period. So what you're going to have to remember is that the formula for period is 2 pi divided by whatever that b value is. B value has a couple of different uses for us when we get to trigonometric modeling. Period is the amount of time it takes for the wave to complete one cycle, but the B value tells you how many waves are completed by 2 pi. So some things to think about. And I don't remember what's on your formula sheet exactly, but we could of course rearrange these formulas if at any point we need to figure out the B value for like writing a function. Then what you're going to do is you'll take 2 pi and divide it by the period. Yeah. Think about that for a minute. The other vocab word, and I think it's probably coming up. Oh, you know what? This screen's a good one to look at right here. Period and frequency are just reciprocals of each other. So a lot of our modeling questions talk about frequency because that's like a more real-life term that we would use. Frequency is just the reciprocal of the period. Therefore, the formula for B is the reciprocal as well. Another formula you might want to jot down here for modeling purposes is if you're trying to calculate the B and you have frequency, it's really easy to find. You just take 2 pi and multiply it by the frequency. So I kind of do like a little, you know, happy dance if they give me the frequency on an application question, which they often do because it's real life. So finding the amplitude, you can find max minus min divided by 2. Basically, it's half the range, if you want to think of it that way, because max minus min would be the range. The vertical shift, or the midline, is max plus min divided by 2, and that's what they wrote here, midline. And then formula for period and frequency, we have that down. Let's see. This is the correct formula here. It is just C if it's in factored form. That's the typo there. Yeah. So like I said, I always rewrite them in factored form. So here's what we're going to do. I think in your notes for class, I jumped ahead and I did all the questions that have no phase shifting. And then we're going to start there. So here's another thing we have to think about. It's not on your formula sheet, but if you think about the shape of sine and cosine, we have like an origin point, if you want to call it that, and then we graph like a max, a midline, a minimum, back to a midline. So after this first point, you graphed 1, 2, 3, 4 points. So what we're going to do is we're going to figure out what I'm going to refer to as the quarter point. And it's basically how far you're going to count apart for each of these max and midlines, because the symmetry of the graph is cut into quarters. So that's the easiest way to do it. And yeah, we are going to have some fraction work here. So we are going to skip around. I think I reordered, or Mrs. Hoffbauer reordered your worksheet so that we start with the ones that do not have phase shifts. So I think this is actually the first one that we're going to practice with on your lesson today. So here we go, graphing, no phase shifts. The amplitude is 2. It's a cosine graph, so in your head if you want to think about what that means. The period is 2 pi divided by the b value. Now this is written a little strangely. Theta over 4 is the same thing as 1/4 theta, right? So that means the b value is a 1/4. Now think about when you're dividing fractions, you're really multiplying by the reciprocal. So 2 pi times 4 is 8 pi. And we're ready to graph. So we don't have a vertical shift here at all, which means our midline's at 0. And if your amplitude is 2, that means it's going to go high and low as 2 and negative 2. So at the very least, we should be able to draw those 3 lines in. So there's no phase shifting today, which means my first point is always going to start at 0. But the other thing I want you to find are what we'll call your quarter points. So you take whatever the period is and you divide it by 4. So 8 pi divided by 4 means that we are going to count by every 2 pi. And if you want to throw a k after it, you can. So starting at 0, we're going to graph our first point, and then we're going to count off by 2 pi's. So this is 0, and then this will be 2 pi, and then 4 pi, and then 6 pi, and then your last quarter point should be the end of the period for these non-phase shift ones, which are 8 pi. So then I think about cosine graph, and where does that begin? Well, for 0 radians, remember cosine begins at the max line. So up here, and then my next quarter point comes down to the middle, 4 pi, back to middle, and then up to 8 pi. And I've graphed, oh, that's not pretty. Just one cycle of this cosine graph, but then they say, please label 5 ordered pairs. So this ordered pair up here is 0, 2. This ordered pair here is 2 pi 0. This guy here is 4 pi negative 2. This guy is 6 pi 0. And this guy is 8 pi 2. Gets a little crowded on that graph, huh? Alright, so here we have a sine graph. The amplitude this time is a 3. There's no vertical shifting. The b value I see is a 2. So if I go to calculate the period length, I take 2 pi and I divide it by this b value. So the entire length of the period for this sine graph is going to be pi. So then the last thing I'd like you to calculate for me is the quarter point. The quarter point says you take the new period, which is shortened to a pi, and you quarter it. So we're going to be counting off by pi is over 4. So here we go. Midline at 0. And our maximum line is an amplitude of 3. So this is 3, this is negative 3. And then if I go ahead and mark off some quarter points, and I count by pi over 4, this is 1 pi over 4. And you know what, guys, frankly, I don't care if you even don't reduce your fractions for this, because at least you can see where they come from. 1 pi over 4, 2 pi over 4, 3 pi over 4, and 4 pi over 4. But, just so we're all clear, 2 pi over 4 is really pi over 2, and 4 pi over 4 is really going to be a pi, which is the length of the period. So now that we're not phase shifting, that should be the end of our first cycle. So sine graph at 0 starts at 0, starts at the middle, and then it's going to travel up to the maximum for the next quarter point, minimum for 3 pi over 4, and back to the midline. Oh, that's ugly. It did not space those out symmetrically. So that was really, really unfortunate. Alright, so now I have to go write out these ordered pairs. This is 0, 0. This is pi over 4, comma 3. This guy is pi over 2, comma 0. Hello. Not negative 0, 0. This one is 3 pi over 4 negative 3. And this one here is pi comma 0. Whew. It's ugly handwriting even for me. Alright. So this one's fun. You have an amplitude of 1/2. You also might want to make a note here that you have a vertical reflection, the negative being in front. So the cosine graph, instead of starting up at the max line, it's going to start down at the minimum line. The period is 2 pi over the b value, which is 3, and there's no vertical shifting. So I'm going to have to figure out the quarter point. If I take the period 2 pi over 3 and I divide it by 4, dividing a fraction by 4 is the same thing as increasing the denominator by a 4. So if I think about 2 pi over 12 and I reduce the 2 and the 12, I'm going to get pi over 6 is what I'm counting by. So, yes. You lucky girl. Alright, go take that somewhere else, please. Alright, so 0 is going to be the start because there's no phase shift. And then we're going to count off by pi's over 6. So 1 pi over 6. I'm okay if you call this 2 pi over 6, but just so we're clear, that's pi over 3. This is 3 pi over 6, which is pi over 2. And this will be 4 pi over 6, which is 2 pi over 3. So this reduces to, what do we say, pi over 3, pi over 2, and 2 pi over 3. Alright, my amplitude lines, my max and min lines, are only going to be a 1/2. Now since there's no like scaling on here, I can make them as large or small as I want. So since I'm labeling them, I'm just going to make them so it's easy for me to graph. Although in theory they should be kind of like a squished graph. And remember it's cosine, so normally cosine begins at the maximum line when there's no phase shift. However, it's been reflected, so it's going to start down here. Middle, back to up. Middle, and back to the lower line. And then it's an upside down or reflected horseshoe looking cosine graph here. And then labeling all these ordered pairs. This is 0, comma, negative half. This is pi over 6, comma, 0. And boy, this is pi over 3, comma, 1/2. This is pi over 2, comma, 0. And this guy is 2 pi over 3, comma, negative 1/2. So I think sometimes there's a disconnect with children thinking that these aren't like graphed functions on a coordinate plane. They really are. Like, we should be graphing these on graph paper. I'm just too lazy to get graph paper. Alright, so here we have an amplitude of 2. The b value is a 1, so the period is just going to be 2 pi over 1 or 2 pi. But the midline, or the vertical shift, has been shifted up 3. So that's going to change, you know, I mean, you can graph it however you want, but if this is 0, your midline is actually up here at 3. That's ugly. And then your amplitude is 2. So that means for us is we're labeling our minimum line at 1 and our upper line here at 5. I still have that amplitude of 2, but now my midline has shifted everything up 3. Again, we're not doing any phase shifting yet. So if I think about quartering the period of 2 pi, that's a real easy one for us to quarter because it's basically the unit circle quartered. So we're counting off by pi's over 2s. So I'm going to label on the actual x-axis because that way it's out of the way at least. But this is 0. This would be pi over 2. This would be 2 pi over 2, which is pi. This will be 3 pi over 2. And this will be 4 pi over 2, which is 2 pi. So we have what? Sine function this time, and sine function begins in the middle. So at 0, it's starting here at 3, and then it goes to the upper line, back to the middle, lower line, back to the middle. You know, I'm getting better at graphing this on the tablet. I just want some major props for that, guys. So this ordered pair is 0, 3. This ordered pair is pi over 2, 5. This is, let's say that's pi, comma 3. This is 3 pi over 2, 1. I don't know if you can hear the movie in the background, but my kids are watching Batman Lego. Alright, 2 pi over 3. So shout out to Batman Lego. Alright, so this one is similar. We have another vertical shift. This time it's going to be shifted down for my amplitude. There's a secret 1 in front here. And then inside the function is cosine of theta over 2. So inside that cosine function, the b value is a 1/2. So you think about what that does to the period. It's taking 2 pi and dividing it by half, which means the period's actually 4 pi. Alright, so graphing. So this is where 0 is. Your midline is actually down here at -4. Isn't that sweet? And then your amplitude is a 1, so your maximum would be up here. Okay, use your imagination on that one, guys. That was really, really not straight. -5 is your lower line. Oh boy. And then taking the period, which is 4 pi, and quartering it. So I'm finding the quarter point right now. I'm going to count off every single pi. So 0, 1 pi, 2 pi, that was easy, 3 pi, and 4 pi. So we have a cosine graph, and it's starting at its normal maximum line here. So at 0, start at his maximum line, and then midline, lower line, back to midline, and back to his upper line. And again, didn't I just say I was graphing so well, and look at me, I missed like all my points. Oh. Alright, so I think as far as examples for graphing basic trigonometric functions without phase shifts, I think that's good enough for us today. The follow-up lesson is going to have phase shifts in them, and it gets way more complicated, of course, when you have phase shifts. So that's probably going to be the most visited lesson, but this is just the general how we get going on graphing basic trigonometric functions. Hope you enjoyed.